someone has to make some coffee before.
Somebody thinks he has time for coffee.
No.
He's
expecting something boring.
Sorry, I completely sank into my Python course and slept through the demo. No, don't worry. There's somebody who thinks he has time for coffee. So.
Oh, okay.
Yeah.
I think that Vienna will not think that way because for him, coffee is not a thing that used to wake you up.
No, the point is that coffee, first of all, it doesn't wake me up. Second, it's a fundamental right. So if you need coffee, you're allowed to go. All right. I think we start.
That's the German equivalent of beer.
So today I wanted to continue talking about containers. We started last time and then we didn't actually finish. I wanted to show you an example of how linked list is implemented using the container random methods. Then we'll go on and talk about decorators and all possible shapes and forms. And we'll implement again a singleton this time, though, using a decorator so that we can apply the singleton partner to another class, to classes that already exist. Without changing it, right? And basically separate the singleton behavior from the logic of the class itself, right? So that's important. So, but first, let's recall what the container random methods are. You have set items to basically call self key and pass the value to it. You have the get items to implement instead of the reading of the item from the collection itself. And then you have the delete items so that you can do del list 5, for example, and you can check with contains. So it contains implement the check if something is there. And you can implement iter to basically create an iterator from your container. So that's basically the theory. Now, before we move on to the rest, I would like to go and look at an implementation of a container step by step. All right. So first of all, maybe a quick, who knows what a linked list is? Yes, from whatever language. Okay. So I'm going to quickly tell you what a linked list is. The idea is that instead of having an array with basically a list of pointers, right? P1, P2, and so on, pointing at the values, you implement the collection in a completely different way. You have basically the array, right? Pointing at the first element, so at value 1, and then value 1 pointing at value 2, and then value 2 pointing at value 3, and so on. So this is what it's called the linked list. And in order to implement this, we need to first create a container that is basically the pointer to the next value and the value itself. And this is what the first class, the class element is, right? So what I'm doing there is just implementing a next and a value. And you initialize the element with just value. And the next is here a bit of primer on the hint type inting in Python. You basically have the possibility to say next should be an element, right? And it should be a keyword argument. So that's I mean, I could have put the next right to the value as positional, but I wanted to show you again and remind you how you can create things like this. So when you put basically after args or after a star, whatever comes after is always a keyword argument. And you can always hint and also give a default value. They're not, none of this is required. You can give just a hint or just a default value, but this still remains a keyword argument, okay? And then you can give the generic keyword arguments. Again, these two are also not needed, it's just for show. So initialization is easy, so call the init and then just go on with the next value. What is on the linked list? Well, the linked list, basically, it just contains a star and at the beginning is empty, right? So when I start adding things, I will then populate star And then I will start populating the rest of the list by adding next to the start and next to the next to the start and so on. So we can go through this very quickly. I don't want to spend time explaining these simple algorithms. This is something that you can read in the code, but it's not that difficult. I mean, basically, we're talking about, okay, get element. If you have a key, first thing we want to check if the start exists. If there's no start, then we have no element. So any key that you are given is going to be greater than the list length. Otherwise, what we do, we just take start, and then we count, basically, in the range of the key that we got. The key is a number, right? So we just count, and we take next every time. And once we finish the count, then we return the element. So L equal next. If we find no next and we're still counting, then we raise an index error. And otherwise, we return the element that we arrived to. So this is not efficient, right? If you have an array implemented with direct pointers, you just take a shift on the pointer array, and then you go to the element. It's O1. This is ON, right? So the linked list is not great for implementing this kind of stuff. Set item, again, not really efficient either. I basically have to go and find the element and then basically put it in. I implement this with the get element because I have to do it more than once. Important is that when I find the element, I mean, leave alone the first that I'm just checking if what I'm doing, it makes sense. But what I'm doing here is just finding, I'm just jumping n times, right? Finding the element, and then I'm basically splitting the element and putting the new value, the prime here, putting the previous from here and putting it on the new element, and the next from the previous element, put it on the element. So I'm just inserting the element in between by changing previous and next to fit the new element. And that's all I have to do. So in terms of single insertion, is actually very efficient because we're just creating a new pointer and assigning the old pointer back. If I wanted to do in the old array, I have to move all the array down if I want to keep the shift mathematics working, right? Get item is implemented by get element, which is this stuff that I implemented up here. And by the way, if you see, this is not a double under method. This is my internal private method. This is the double under method, which is just return itself, right? But the difference is that the get item returns the value, because when I make container brackets 5, I don't want to return the element. I want to return the value of the element. I don't care about the index. So I implement this extra step so that I can reuse this function because it returns me the element, and I can use it, for example, for set item, because here I am using the element itself because I want to change the pointer, right? Important. So I'm not returning the value. With the value, I can do anything. I need the element so that I can change the next. The iterator is quite easy. We just start with start, and then we just go on until we don't have any more value, and we yield the value. Important. We don't return it, we yield it.
What exactly is a yield?
So if you do a for x in container, right? Then if you from the container you yield, you basically for will get the next item, but then when it asks again for one, we'll call again this yield. So the function stays operative basically and keeps giving you results without exiting. All right. Just very, very unorthodox explanation of yield in an iterator. Right, string is nothing else, just some gimmicks to print a nice way, in a nice way, the array, and not to have 1,000 elements on the screen. I'm just putting ... after 10 elements.
Can you use the item method inside the get item?
The item method inside the get item, absolutely, I could. The only thing that I need to be careful is that I don't have cyclic references here, but I don't. So I could totally get this. I could totally do this. The problem again is that here I'm yielding EL value and not EL item, so element. So I need something that actually returns me an element. But it could be actually simplified a bit. I could actually build the element iterator and then get the value out of it from the wrapper, so to say. That would be cleaner even. So string is quite easy. Length is just counting on until I have elements and returning the count. The del item is a bit involved. Now, if you're deleting something, you have basically two options, and I will see that later in the test. Actually, we can see that right here. So I can always pass a slice to my deletion or to any actually bracket. This, for example, means every even index. And I need to cope with this kind of slices when I actually implement my del item. Actually, I should do it also for the get item and so on. Just implemented it for the del item for now so that you can see what it means. So there are basically two possibilities. Either I get a slice or I get a normal number or a normal key, right? If I get a slice will return to me through this nice method indices, which I have to pass a length, will return to me the three things that I need for a range: the start, the stop, and the step, right? So if I run this, let me do that. If I run this, I get 0, 100, and 2, because in my list I have the first item is 0, the last item is 100, and I have a step of 2 because I selected all the even elements. So that's this double column 2 means all the even elements. Once I have these indices, well, I print them, that's what you saw. But what I need to do is to be very careful. If I want to delete from a list, right, I better start from the back. Otherwise, my index will change. If I start from the front and I start deleting items, what was 5 will become 4, and then all my ranges and indexing will go amiss. So what I'm doing is I'm reversing the range, and then I'm deleting the single items one by one, starting from the back. Does it make sense? All right. So otherwise, I just delete the single item. The single item deletion is easy. It's just finding the item, removing the item, patching the next and the previous together so that I don't have all, and moving on. Simple example. I've just created a list with 100 elements, and I am deleting all the even numbers and printing the list. And that's what you saw right here. So start with the list of 100 elements, deleting all the even number. I get all the odd number, and I have 50 elements in the list. That's pretty much it. Okay. Yes?
So
there's no dumb question.
Link. So what is advantage for using link compared with I have everything in a way?
So the linked list is useful because it's very easy to transverse, and it's very easy to insert to append new items. And even inserting is actually, append from the start, append at the beginning. And even inserting is actually quite easy because you don't have to move the objects in the array. But this is probably better a question for Andrea after the lecture. I don't think there are so many implementation of linked lists nowadays. I mean, this is not really an efficient way to do things. Just wanted to show you with a classical implementation of a collection how you actually would do it with the dunder methods. What you usually do is, if you have a list, you just use a list implemented from the OS or from the interpreter, from the compiler, from whatever library you're using. I mean, you don't mess around with this stuff because you're never going to get something that is more efficient than what is in the standard libraries, right? I mean, unless you are somebody that writes those for as a job. Any other questions about this or about containers? We can move on to decorators.
How is it implemented internally? Is it ref counted? Is every object internally ref counted?
So Python implements two ways to do let's say, garbage collection. One is ref counting. So every object has actually a header field, so to say, that has the ref counting inside. And then as though a second way to garbage collect, which is actually a garbage collector. And that happens when you have cyclic references. So to take care of those, there is a periodic garbage collection that can kick in at any time and remove your basically circular references that are not, connected to anything anymore.
Okay, thanks. One more question about the is instance. So in del item,
Yes.
it's in del item, yeah. You check it if it's an instance of a slice, but slice is not written in capitals. I thought slice would be where's slice coming from?
Yeah, that's basically also int is not in capital, right? It's still a type. So yeah.
So slice is a type, or
Yeah.
not a variable that was hidden somewhere.
No. Slice is a type, and it's basically the slice type is what you've written inside here. It's just an internal type. Yeah. No.
Okay, thanks.
I thought for implementing and iterating, you just have to implement the double underscore next method.
Yes, you could do that as well.
It's the same.
The double underscore next is used. I'll answer this next time a bit in detail because there are some differences. Just don't want to say something wrong. Anything else? All right, then let's go to the rest of the presentation and let's start again. So we saw this, and next we talk about singleton. Yeah, why singleton? Don't remember, but let's talk about singletons again. Just I think there is a review from last lecture. So singleton, again, unique instance per process. If you start different processes, you're not guaranteed anymore. In Python is usually implemented with new and is useful to control other resources or factories or database connection or anything that is connected to something that you need to keep a watch on. And we'll implement this in a decorator. But first, what is a decorator? The decorator is basically just syntactic sugar. So this is all there is to know about the decorator. This thing is equivalent to, let's see, is equivalent to this. Then I was too eager. So basically, there is nothing else to know from a language perspective about the decorator than what's on the screen. You basically have a syntactic sugar that you can place on top of the function definition, and this translates to the definition being passed as a parameter to another function, which is the function name decorator in this case, right? So, and that's what it is. That's nothing less, nothing more. You can pass a function, you can pass a class, and that would still work. Yes.
The question that I want to ask also last time. So, what is syntactic sugar?
The syntactic sugar means basically that it's a nice way to do the same thing that you could have done differently.
Okay.
Right? So it's basically a piece of syntaxes that you can use that doesn't change the functionality, but it makes it nicer. Right?
Nicer means look nicer.
It's readable. This is a lot less readable than this. You'd agree with me, right? No, he doesn't agree, but that's okay. Those are C programmers, and that's fine. Anyway, so that's all there is to know. The question starts when you say, okay, I want to implement this function. Now, how can I implement it? How can I use Python to implement the decorator and make it look, nice and do what needs to do? And that is important. I mean, why is it important to implement decorator? We see in this last time. Let me remove this. I've lost my cursor. That's nice.
Can I actually use more than one decorator on top of a function?
Yes.
Okay.
So there's staples of decorators in complex programs because you want to basically do authorization as a decorator, you want to do net publishing as a decorator, and so on and so forth. So you basically write the logic of the function, which is probably very small, and then you start adding all these things on top, and we'll get to that. I mean, one of the things, why decorators are important, because you can basically separate the main function of what you're doing from all the other stuff that you need to do, like controlling if the parameters are well formatted, like controlling if the user has access to this function, or if for whatever reason you have the valid token, or anything that is related to authorization. Publishing to the network, publishing to database. I don't know. I mean, there's a lot of things that you can do within your function, must be done within your function, but they are not the main function of the function. They're not the main goal of the function. And if you start adding all this code, we'll end up with something very long, very unreadable. So the idea of using the decorator is to separate this functionality, put it in another function, but reuse it right there where you need it, and document it the same way, right? And this is, if you come across this this statement, cross-cutting concerns. Cross-cutting concerns is something that has been used a lot in almost, it's not anymore so famous aspect-oriented programming, but was famous 10 years ago, and there's a lot of implementation, particularly in Java and Aspect-J. Cross-cutting concerns is what this whole thing is trying to solve. Basically, again, authentication, authorization, parameter checking, and so on, in a way that you don't have to pre-implement it everywhere, because these are not functionalities that you need to implement in a module. They are cross-module usually. So you have to either copy paste or start calling different functions everywhere. A lot of boilerplate code. Boilerplate means stuff that you just have to write. It doesn't mean anything. You just write it everywhere, again and again. And yeah, so how people tackle this is totally different topic. But one of the ways to do this, which is a bit more simple than what was implemented in Aspect-J, for example, is using decorators. Yeah, so authorization, as I said, validation, and also it can be used to augment classes, right? So if you have a class and you want to implement some, for example, getter and setter methods on your variables, you can pass the class to a decorator, and the decorator can implement those getter and setter methods for you. So there's things that you can do there. Implement design patterns like the singleton that we are seeing later. And yeah, again, so what is a class decorator? Just started with the class already, but so you can decorate a function. You can also decorate a class. It's the same concept. You take a class, you pass it to the decorator modifies it, and then pass the class back, right? And this is how it's used. Nothing more than before. You can add, remove, override members, right? Can do whatever you want. The class is passed to the decorator, so we have freedom. What is important, it does not participate in class inheritance. So if you decorate your class and then you ask whatever super is, it's not my class, it's actually the super class of my class. But the decorator doesn't appear in class inheritance. So you cannot use super from the decorator or do things with class inheritance. Any questions on this? Sorry, before I go on. All right, so let's pass to decorator factories. This is annoying. All right, so the problem arises sometimes when you want to parameterize your decorators. You want to say, okay, I want to, for example, let's say a function returns a string, and you want to assure that the string is not longer than 20 characters. Well, maybe you want to put a parameter and say, okay, the 20 characters might be 10, might be 15, you know? So this is something that the function doesn't know, and you have to pass to your decorator before you can use it on the function. So these are what is called decorator factors. It's not actually just a decorator, but is a function that creates a decorator, which applies then the decorator to the function and returns the decorated function. All right. So the idea is to implement something like this, for example, for a class, and the parameter one gets processed by the decorator before the decorator, by the decorator factory, before the decorator processes the class. Make sense? All right. It is equivalent to a function returning a decorator. I mean, this is again equivalent to this. All right. So there is an intermediate step. We first define class, then we define, we actually call decorator factory with the parameter. and this returns to me a function. The function then is applied to my class. So this is basically the equivalent of what's happening up here. And it makes sense, right? I mean, the add just transformed this into a function called calling this. So this, including the parameter and the call itself, must be a function. So this must be a function, and then I apply the function to my class. Nothing has changed. Again, it was all introduced in the last slide. There's nothing new here. It's just in another iteration. Question about decorator factories? All right. Yeah.
Quick question. Sorry. So if you input different parameters, that decorator factory can output decorator for the class, also can for like for the function, right?
So if you input the different parameter here, depending on the implementation of your decorator factory, you will output a different function, right?
Okay, yeah. Then these different functions can use for decorating class or function.
Yes, you can decorate with this pattern. You can decorate with a class or a function. There's no difference there, right? So that's fine. We'll see later that to do this with a function, you have a bit of an annoying structure, because you have to define the decorator factory, then define the decorator within the decorator factory that gets returned. And within the decorator, you have to define the wrapper function or class that actually gets returned by the decorator. So you have a 3 times nested syntax, which is annoying to read, particularly when you go into indented code of the implementation. You know what method it's from the decorator factor, from the wrapper itself.
Question?
Yes.
So what is the advantage of using the decorator?
The decorator factory is used basically when you have to do exactly decoration of functionality that depends on some parameter, right?
Compared to defining the decorator factory alone and then having basically.
Well, I mean, you can also define it as a function and then call it as a decorator. That's fine. But in the end, to simplify the syntax, you want to define the decorator within the decorator factory, in the scope of the decorator factory. And again, to simplify the syntax, you want to use the parameters directly inside the decorator to define the wrapper of the final function. We'll see an example, but the point is to have access to all the scope variables within the scope, you want to implement it in a nested way, right? But since that gets complicated, there's a second way to do it, and this is using a class, so decorating with class. The point here is that the class we learned can be called an object, can be called with the called method, exactly like a function, right? We can implement call, and then our object acts like a function now. So the advantage here is that we have init that we can use. So instead of using a decorator factory to initialize our parameters and then returning a decorator from within the function that is implemented decorator factory, we can implement init to initialize our self members, and then use self when we use call to actually do the right thing on the decorated function. Does that make sense? So instead of nesting, we're using the class structure. So we do the decoration factory here and the decoration call. And to my taste, is more readable and understandable than actually a triple nested function. So that's it for slides. Let's go actually to the interesting part and start with the simple decorator. All right, so there's nothing much here. I'm just showing you how the decorator is defined. So I have a typical structure, which is the decorator that takes a function. And then I have what I usually call, it's usually called the wrapper function, right? This is not the original function. I'm not actually taking the original func object and modifying it. I'm putting actually a new function, defining a new function, and I'm using the func object within the new function, right? But this is important because later we'll see, for example, for classes, we can do also the other way around. We can actually, instead of wrapping the class in a new class, we can actually modify the class right away. But in this case, we're not. So I am defining the decorator like this, which is basically taking the output of the function and just writing decorated at the end. It's just a simple example. And then I'm just defining it like this. I'm just defining my function in this way, decorating it with decorator. And yeah, to show you that it's the same stuff, I'm just also calling it, defining a similar function, but without the decorator add, and then calling it through the decorator function. Be careful what the parenthesis is, right? So first, the decorator is applied to my func2. This returns a function, which is then applied to C. This is even more explicit. I'm just defining a function as a return of the decorator and then applying my func3 to D. So let's see what happens when I call it. Nothing much. Decorator works exactly like the other two calls. Any question in this? Okay, let's move on. So a class decorator. That's no wrapper. I'm taking the class and I'm adding a method bar to the class, which just returns bar. And that gives me also a chance to introduce lambda functions in Python. So instead of defining a function and then using it as and assigning it to bar, I'm just writing lambda x column the output. So this is shorthand to just define an inline function. And then I'm just returning the class as it was, the same object. So if I now I use the class decorator on top of my new class foo, which has nothing inside, I can use the class foo, instantiate it, and call bar on the object. And lo and behold, it actually works, I think. So, and there it's our return, right? So different behavior. In one case, I used a wrapper. In the other case, I'm just modifying the object, but it's the same pattern. Any question? No. All right. So let's see how can it be actually useful. So let's suppose that you have a database, for example, and you want to read from this database row by row. And you want to make these rows accessible as objects, right? So the database is defined outside of your code, but you want to create a simple interface, and you use a structure like this one to define. You say, okay, this is my table row from this particular table, and I have two int field and one string field inside, and they are defined by these classes, right? So, and that's all you want to write. You don't want to write the methods, every time, like get my int one, get my int two, and implement it there. You want to implement it centrally somewhere, and then apply it to the classes depending on what fields are implemented in the class that, are then in the database itself. So what you can do is create a decorator that basically parses these fields, these class members. These are class fields, right? And not in the object, they're in the class. And then adds methods to treat those fields from the database in the way that you choose. Make sense? All right. So in this case, our decorator will take a class, and then there's a bit of tricks here that because I'm modifying the items of the dict of the class, I cannot actually iterate directly in cls.dict. I need to copy this dict to another dictionary, then iterate it through the other dictionary while I add new members to the original dict of the class. Does it make sense? All right. So basically, after making a deep copy of my items of the class, I just go through them. I check attribute name and the attribute. So this will give me all the functions, all the internal members, everything that belongs to that class. But I'm only interested in int fields and string fields, Because when I find an int field, I know that I have defined it like this. Then I want to just take the name of the field, because this is by convention the name of the column in the database, right? And then create my getter method to extract data from the database. In this case, it's just returning a 1, but here you could basically implement all your database stuff. And what you're doing is basically checking if the instance is the need field, creating a getter, and then assigning the getter using setAtt to the class, creating the name dynamically, so get whatever the name of the field was, and then setting the function as implementation. And this way you can use a decorator to implement all sorts of different things that come to your mind if you have to dynamically do this stuff at runtime. Questions? All clear? All right.
So basically, this is the compact way of inheriting the base class each time and defining the types of getter, setter for the specific instance that you have at hand.
Exactly. So if you had to implement this in pure object-oriented, what you would do, you say my table row is table, and then you would have something that overrides standard methods or call standard methods and implements these stuff statically instead of dynamically. So you would have get int one, get my int one implemented, and you would just say read field name int one from the database, and that would be implemented centrally. That would sort of be the way to implement it in an object-oriented, but it would be a lot more the boilerplate, right? We'd have to implement different methods and so on and so forth. You have to know which methods to implement, while this basically can implement not just the getter, but the setter, counting, length, anything you want.
How many times are the decorators being evaluated?
At only when you create the class. So basically, this is evaluated once when you define the class. The moment that this code is interpreted, it gets called the decorator and returns the decorated class instead of the original one.
So it says you send and start.
Yes. Static.
Oh,
I mean, it's an object, right? So, right. So, in the example, I'm just, creating a new myTable row and calling the two methods. There's not much to see, but just to see that it works. And it's returning 1 and a, as I was calling first my int 2 and then my string 1, right? And these are defined here, my int 2, my string 1, just happens to work. Nothing major here. Any other question before we move on?
Yes, is it the right way of whatever it is called in Python to do such things, or is it simpler to have a class myTable row that comprises 2 ints and a string and not all these meta programming?
Depends on the editor, but I wouldn't hold my hope high. All right, so let's move on to the next topic. And in this case, we are looking at the decorator factor, which is what I was saying before. So the typical decorator factor has this particular structure. You have a function, which is the decorator factor, which returns a decorator. The decorator itself returns a decorated function, and the decorated function uses the, this is wrong, uses the function 1. Yeah, I mean, no, this is fine. So the decorated function, I get confused because there's so many calls. The decorated function actually takes the same argument as the function itself and returns another output based on the function and on the argument and on the original parameter of the decorator factor. So let it sink in, stare at it for a minute, and I think you will get it, right? So I first define my parameter. I then define the decorator, and I can use the parameter inside. I then define the decorated function, the wrapper, and I use the function that I get passed from the decorator inside that. I return my output using the function, the parameter, and the argument of the function. I can use all three. And then once I return the function, I return the decorator that returns that function, right? So The decorator factor returns a decorator. That's the only thing it does. The decorator that returns a decorated function. But it gets hard to read, particularly when it's not just a short and you have stuff inside, particularly if it's a class, right? So the way it works is pretty simple. You decorate, sorry. So this decorator just prepends whatever parameter I put here to the output of the function. And so I would expect to have foo column f arg1, right? Where arg1 is whatever I pass to the function in the output. And yeah, I mean, this is the same as doing it differently by defining decorator where dec factory foo and then applying the decorator. That's just the same stuff, just explicit instead of nested. Tell me when you're ready. You go through that. Yeah.
Quick question. So why do we use this inner function? What is the benefits of using this inner function?
Right. You can't really change a function. I mean, you can, it's an object, but it's very hard. It's very unreadable. If you want to actually change the output of a function using the function itself, the best way is to produce a wrapper, a function that calls the original function and then does things with the output or with the input. You can also process the arg1 before you pass it to the function, to the wrapped function. For example, if you want to do validation of parameters, you would do it the same way. You just would, here validate the parameters between the def and the return, and then only if the parameters are valid, you would pass it to the original function. Otherwise, you would just raise an exception. And this is the kind of things that you do in a wrapper. So you implement other functionalities, and then you pass it to the function, take the return, implement still other functionality, and then return the modified output, which could be, for example, HTML encoded for strings, or could be anything else. I mean, you basically have freedom to change your returns as you want. So that's why you wrap the function in another function, right? And then, yes.
What's the main benefits instead of in the HTML example, from just calling another function from the function which would input output?
The main benefit is consider that you're doing a class that just collects data from a database where you have customers. You have first name, last name, and all this addresses and so on. Now you don't want that HTML things to be there every time, right? The HTML encoding. You want them to be there when you're actually using an HTML output when you're printing to a web page. So separating the function calling of the HTML encoding and decoding from the implementation of the class itself makes it possible for you to use it both ways. Also, the HTML encoding or whatever post-processing you do to the data is not really part of the logic, is it? So it simplifies your code by putting all this extra, again, cross-cutting concerns somewhere else. You take care to test your decorator once. You know that it works and whatever output it is, and you know how it's working, it's documented, and then you just care about the logic of your program and had it where you need it. Make sense? All right. So yeah, I mean, if you call it, it's nothing major. I mean, it's just adding foo before the output of the function. This is the decorated with the at, and this one is the explicit call. Works in the same way. It is the same thing. It's just again syntactic sugar, right? Any question on this? All right. So now we can look at the object-oriented way to do the same thing. So this, instead of having a nested function within a nested function within a nested function, as a class which uses the init to create the self parameter 1 equal to foo, and then in the call, it actually uses self to get access to this parameter. So it's the same concept, it's just using the object-oriented way to implement one of the nest calls. In the end, you have also 3 nested calls because you have the class, you have def, and you have the second def. So you have actually 3 times nested implementation. But the fact that there is a class and it separates the init from the call, it actually simplifies the reading as well. Nothing major except from that. Any question on this? Any particular thing you want to? I mean, one of the first thing that was unclear to me when I started looking at this kind of stuff is that the init takes the parameter of the class of the decorator factory, and the call takes the function to be decorated. For me, it was not obvious. So it's important just to remember that this is an object-oriented decorator is nothing else than a decorator factory, and that the first stage is the init, the second stage is the call, so you don't get confused. The parameters of the decorator factory go always in the init, and the parameter of the decorator, so the function itself, goes in the call, right? I mean, that's the basic. Once you have understood this, then the object-oriented decorators, it's really easy to get your hands around. Right? If you were decorating a class, you would have a class here instead of a function in the call. But all the parameters, like, okay, I want to, I don't know, pass the username of the user that has access to this class, that would be in the init, because I want to save it and reuse it every time I call the decorator, right?
Does this have the same cost?
Yeah, I mean, and then I can decorate it pretty easily by just adding in here, say calling parameter 1 equal to foo, and so on. Here in this case, for example, I use this particular syntax so that param1 is an explicit parameter, it's a keyword parameter, which is putting a star and then putting the name of the parameter. So if you do this, this is not anymore a positional parameter, it's a keyword. It needs a required keyword parameter. So you have to put it, but you have to call it like this. And it's a lot more readable, particularly for the decorators. You don't want to have positional parameters because, yeah, I mean, people need to use it. They didn't write it, so that you might want to have the documentation very explicit in the code. That's why you use keyword parameters. Keyword parameters explicit the documentation. You don't get confused. Does it come first? Does it come second? What parameters can I use? It's in the name, right?
So can I understand this way? So decorator is talking understand something, some add-ons for given function.
I'm sorry?
Some add-on.
Yeah, these are add-ons for functions. So if again, pre-processing, post-processing of functions.
Yeah, again,
When it comes to functions.
yeah, again, so then this is nothing. So the decorator is also nothing other than a function.
It is no, it's not just nothing other. It is a function.
It is a function, and you call it decorator.
You call it decorator because of this syntactic shooter,
Okay. Yeah.
the add that I put on top, but it is a function. There's nothing else. The first slide was everything you need to know about decorators, right?
I just want to double check saying so. There's an idea in my mind is that is there something you create a function, you call a function, and then you do something on top of this function, and you get the stuff.
Yes. So you again, it's a function that processes a function and gives you back a new function that has some more stuff inside. There's nothing else. The reason we use it is to separate this stuff that is not part of the main logic, pre-processing, post-processing, access control, and so on and so forth. Right.
That was something that need to also be used by other things, and they can be used.
Right. You want to use access control all over your program, right? You don't want to use it just in one module, and you want to have an easy way to put it and to document it. So you don't want to just rename the function a new function and put the arguments that, you know.
Now is clean my structure. Go back to that point for syntactic shooter. Yes. Yeah.
Right. So that's basically the difference, right? So then we spend a little more time on the last decorator that I wanted to show you, which is the singleton. Now, this is, before we step into this, we're going to try something different. Let's see. Yes.
You have to turn on the mic. Okay.
Oh.
Hi, can you hear me now?
Sorry, guys. There was a question?
Yes.
Okay.
Can you hear me now?
Yes, I can.
On the previous slide,
Yes. Program, you mean?
yeah, the previous program.
Mhm.
Does this have the same costs or complexity or implementation costs as the previous decorator, to doing it like using the object-oriented way? I mean, of course,
it's a bit. I mean, it's a bit more expensive because it goes through the life cycle of an object with a class, right? The function is just one code, and it returns the decorator. This one goes through new, goes through init. So there might be something more, but usually, again, it's, if you're caring about how expensive it is to call it, then probably you should implement it in Python.
okay, I'm just asking this because I have seen some interesting initializer constructs in JavaScript that look quite similar like this, like overriding anything. And it in the end, it was so complex, it took about 50 milliseconds to initialize the whole stuff. And it was meta programming stacked on top of meta programming, and it was in the end very slow. But to unravel this and understand why it was slow, it was to get into the JavaScript complexity, and it was a lot of string parsing. I'm not sure, is this the right way that you use in a high performance application, or is it just for me to, where do I use it?
So
In a high performance code or not?
Put it this way: if this is the bottleneck, then you shouldn't use it. Usually, I've seen this stuff used in libraries. You don't use it actually. Not many cases where you have to write it yourself, but it's important, I think, to know if you write in a library how to do it. And I saw that used a lot where, for example, the main functionality is reading some static file or accessing a database or accessing the network. In this case, there's so much latency from the actual operation that you don't care about this part.
Understand, yeah.
Python is a bit more efficient than JavaScript usually. That's also the case. So the base functionality in Python is implemented in C, and it's quite fast. When you when you implement something like this, whatever you do inside, like string manipulation, is fast. The thing that you shouldn't do is actually call this in a huge loop that gets processed every few milliseconds, because of course you're going to see the hit. Make sense?
Yes, thanks.
We can use lambda instead of the linear decorator, right?
Yeah, absolutely. You can actually return lambda, xf, and so on. Right? I wanted to show you this in two different ways. This is with a wrapper. The other one is with the lambda. You can do both. The lambda is the wrapper in the case. Any other question about this? And sorry about the microphone. Right. So let's move on to the singleton. Actually, I was thinking about doing something, but I'll just go through the code with you. So if we want to implement a decorator to create a singleton out of the class that we just wrote, without writing the singleton code inside the class, but writing in a decorator, then what we need to do is re-implement new, right? I mean, this is one way. There's many ways, but one way is to do it with the decorator that re-implements the news. And the new does the checking if the instance is already there, and if it's not there, it creates it, and then it sets it into the class, and then just returns the instance. If it's already there, it just returns the instance. It doesn't do anything else, but it's not that easy. If you re-implement the new in the decorator, and then you call, type, for example, or super, or whatever you want to call there, what you end up with is a loop. Endless loop, because the type creation will remember, the decorators are not part of the class inheritance, so I cannot call super and go to the next class and do that there. If I do type here and I pass it the class name, it's going to look what my new is in full, and then call this code again, and this will call the type, and we'll end up running the loop again and again and again, right? And at some point the interpreter says too many iterations. So what you need to do, again, this is one way to do it, and mostly I'm showing it to you because I want to show you some cool features that Python has. What you need to do is actually to trick a bit the class to be something a little different, do the new object creation, and then substitute the class back with the original class. So what we are doing is creating a deep copy of the dictionary of the class, of all the members and the functions and everything that we have there. then using type, then removing new from our deep copy so that the new class doesn't have a new implemented, all right? And then we call type creates a new object, and it takes the name of the class, the basis, so whatever the class super is, right? So this basis is basically a list with bar inside. Bar is the superclass of full. And the attributes, which is our CLS dict, all right? So when I pass this, the interpreter will create for me a new object, which has a class, the same name as full, same basis, same functions, except for new, which is not there. Once I have my instance, I just replace the class with the original class, right? And then I return it. Questions so far? All right, so this is my new function. What I do then in the decorator is I assign this new function to new in CLS before I return CLS. And that's why the infinite loop is there. Because once I get to instantiate this full here, I am calling this new because I'm not using the original class. I'm using already the decorated class because it was returned from here already with this new assign. So I need to be careful when I am inside the new to not iterate again. Make sense? This is not the most elegant way to implement it, but I wanted to do it this way also to show you the kind of little things that you run into if you start implementing, class modifying things on the fly. You might run into infinite loop, you might run into inconsistencies and so on. You need to be careful where you actually put things, where you remove things. So in this case, that's basically all it is. Well, the class itself is just incrementing with this counter, and then I'm just printing incrementing and printing the values to see if it's actually the same instance or not. Questions on this before we test it?
Quick question.
Yeah.
So that attribute class, like download class, that attribute is only exists after you create an initialization of instance of the class.
So every object has a class. A class, usually, if you call, for example, full class, the answer would be type. Type is the class of every class, unless you refine a meta class. So the class is always defined.
Yeah. So if you already initialize a class,
Mhm.
then you call this some class, then we will return the type of your
Instance.
Yeah.
I call it in an instance. If I call it on the class, it's going to return me type. If I call it on the instance, it's going to return me the class. It's going to return me basically this usually, right?
Yeah.
But in this case, it's not, because I have substituted the instance with something else, and then I'm returning that thing. But now I am assigning back. So the point is that here I want to put the things back as they were. If somebody tries to call my new again, it will not run into infinite loop, and at the same time with respect to singleton pattern. So the reason I do this is because if I were to use, for example, a dot class parentheses, if I don't do this, this will generate a new instance. You understand? Because the class that is inside doesn't have the new implemented. So it would just generate a new instance starting from the full definition, which I copied very vigilantly with every basis and methods and so on. It will use all those things, but not the new, and will generate a new instance. So to avoid that, people use existing instances dot class parentheses to create a new object. I just substitute back the original class into the class. And then I'm sure that it will go to my new every time. And if it goes to the new, the second time we'll check the class is already an instance. So I'm not doing anything, returning my instance. Make sense? So where's the weakness of this implementation? What happens if I implement an init here? in full. Even worse, what happened if I implement it in bar? Gets called every time. Every time I get a new object from full, it will call init again and again and again. So the init must actually check that the instance has been already created. So to implement this properly, I should actually also override init here and make so that the init keeps track if the class has been, the instance has been already initialized or not. So I should check to keep another state variable implementation, check if that has been already processed, and then process the init or not. Make sense?
Can you just remove the init afterwards?
You can, but the init might change your class, might assign new values, might reinitialize some of the values that you don't want to initialize and so on. So you don't want to do that. You want to basically here gather the init from the original class, wrap it around with a new init, check if the init of the original class has been already processed. Maybe if you keep in a status variable in the singleton wrapper up here, where the CLS instance is, right? To define status, you know, init processed false. If init processed equal false, then process the init. Otherwise, just skip it. If you don't do that, the init will be processed every time. Any question? Right, let's just give it a go for kicks. So first of all, let's clear and let's rerun it from scratch. I am creating an object, incrementing the first object, creating a second object, incrementing the second object, then incrementing the first object. And then I'm printing the counter, the object A, the object B, and the class of A, right? So that's the output. There's also another print somewhere up here. I don't know where, but the point is it's always the same. So as you see, the counter is 3 because I created, I called the increment 3 times. I created 2 objects, but I called the increment 3 times in the different objects. They all incremented the same instance. And the fact is that if I print the 2 objects, I get exactly the same object. This is a simple way to see what your object is. This is a full object and this gives you the memory allocation, right? So you see it's the same object. And then if I print class, it will give me full, which is what I expect. It's the original class that I want. Again, the decorator doesn't take part in class inheritance. So the interpreter really believes that that's the class foo, whether I decorated or not, it doesn't know.
Quick question.
Yes.
Regarding that memory address problem, so when you create a new function or you're doing some operations, then the memory will be randomly located to some variable or just follow some rules.
I don't know how the internal memory allocation works, but the point is that whenever you have an immutable like function and you modify this this function, 2 things can happen. I mean, one is that you get a new pointer to a new function implementation. For example, if you have a wrapper, or if you have a class and you add a method, you keep the same pointer, but then that's not immutable. It's mutable because you have basically within the class a pointer to a new method that you didn't have before, right? So that's what happened. What's happening in this case? I'm just making sure that it's the same object. So if you look at this, what I'm printing is A, and I am assuming that A and B are nothing else than CLS instance. And the other print was here, print CLS instance, and you see that's the same output, right? So let me see. Oh, come on. So you see the CLS instance, the first print, it's exactly the same as the print of A and B. So what I'm checking here is that the object that I have in my A, B is the same as the object that I had in the decorator for CLS instance and nothing else.
Okay, another question.
Mm-hmm.
I just curious about how the memory and CPU stuff working. So you have, when you are implementing something and running something on the like your computer,
Mm-hmm.
you create a different object or different variable. does the first function maybe allocate the memory to the first function and the next function and the next one?
Right, that depends on the interpreter on the particular implementation. In Python, these are objects. All of them are objects. So what happens is that when you define a new function, a piece of memory will be allocated for you. That the code will be saved in that piece of memory, and basically you get back a pointer to that piece of memory. And this pointer is in your scope. And whenever you want to use that function, you look at the pointer, look at where this piece of code is, and it gets interpreted. Right?
So, okay, the pointer is the most important part. So where it is, it doesn't matter. You can just get according to its pointer to get where it is.
Right. I mean, in Python, basically everything that you allocate is in the heap. That's what it's called, and it's dynamically allocated. So it doesn't make much of a difference. In other languages, you have a difference between, for example, if you allocate an integer within a function, or you allocate an array within a function, they are treated very differently, right? And that goes beyond what we want to discuss here, but the point is, in Python, you don't have to care about. There are some optimization usually done in the virtual machine that we're not going to touch, not for now at least, right? Anything else? Otherwise, I would say we are almost in time to finish. Alex, you're still there? Just in case you had a question, just want to check.
No question from my side.
Okay.
I'm
great.
just, I feel decorated.
All right. And with that, I think we can close. Thank you so much.
Thank you.